Okay, this is going to be the introductory video on the Lagrange remainder of a Taylor polynomial. And if you look in your book, you'll find this definition of a Lagrange form of the remainder. And all we're going to do in this video is, rather than solving a specific problem, we're just going to go through and try to understand what each of the different components of this thing is and what it looks like. And also we'll look at it graphically so you can begin to see graphically what this means. And hopefully by the end of the video, you'll understand what each part of this definition means. Now, this is the Lagrange remainder, but normally when you look at this, let's take a look at a comparison of one other thing. So I've got Lagrange remainder definition over here, and generally you'll see this. If you look in the section of your book that has the Lagrange remainder, somewhere close to it you should see this, something called Taylor's theorem. And they're generally right next to each other. And as it turns out, if you just look at them, they look, in some respects, there's some differences between them, and they're similar in some respects. And by the end of this video, you'll see that the Lagrange remainder is really nothing but a variation of Taylor's theorem. So we'll spend quite a bit of time on this, and then we'll show where the Lagrange remainder comes from. So that's going to be kind of our goal as we go through this. So let's go ahead and begin, and we'll try to develop this thing. Now, to start with, we want to do this. We want to understand where the Lagrange, or each part of the Lagrange remainder, comes from. And we'll begin with some f of x, and we'll do this graphically so you can picture what's going on as we go through. So first of all, suppose it is. I've got some function f of x, and that's going to be this blue line right here. Now, just to number it, I'll go ahead and put f of x here. So that's going to be my original function. Now, I would like to estimate this function using a Taylor polynomial. And for most students, if you're just now getting on to the section on Lagrange remainder, that should mean that you just finished the section on using Taylor polynomials to approximate functions. So what I want to do is to approximate f of f using a Taylor polynomial. And let's go ahead and take a look at that rule. So this rule should look familiar to you if you just finished Taylor polynomials. Now this is going to be a Taylor polynomial centered at x equals c, and it takes this form right here. So first thing I'm going to do is just write out the terms of this thing, but I'm going to cheat just a little bit. I don't want to write out all these things individually, so when I write them out, I'm actually just going to use a little square to represent each one of those terms. So it'll look like this. I'm going to say that f of x is, and I'll use initially approximately equal to, because I'll use a fixed number of terms. So I have something like a first term plus a second term plus a third term plus a fourth term plus, and I think I'm going to do this, is I'm going to actually stop with a fourth degree polynomial in this example. So I'll go back again, and that last term actually looks like this term right here. So this one I'm going to go ahead and write out, and you'll see why here as we go through this. So this would actually be f sub n. So the nth derivative at c divided by n factorial times x minus c to the n power. And all that is just the last term of this thing right here. Now, if I stop my polynomial right there, I would have this. I think I'll do this in red here. What this was the n is equal to 0 term. This was n is equal to 1, n is equal to 2, n is equal to 3. And in my particular case, this was n is equal to 4. So I had a fourth degree polynomial. So I'm just going to put a bracket around this, and all of these terms together would be given by this notation here. So I've got a p sub n of x. And this red term represents the polynomial. Now it's a fourth degree polynomial, and just graphically, let's see what it would look like if we graphed it. So if I were to graph this thing, it would take possibly the shape of this red graph right here. So what this is going to be p sub n of x. And in my case, it is p sub 4 of x. So I've got a fourth degree polynomial that I'm using to model this thing. Now again, graphically, let's write down kind of what we know about this thing so far. The actual value of f of x, and what I want to do is this. I'm going to center it at 1, so c will be 1. I'm curious about when x is equal to 4, so I'm going to evaluate this thing at x equals 4. Now, if you just had the blue graph, if you could actually see the answer, the exact answer will be that right there. And you can tell the exact answer is going to be 6. So what this is, if I went from here, and I think I'll actually just put it on the graph here, from here down to here, this would be f of x. So that distance is going to represent f of x, and that's what this is right here. And you're going to approximate f of x with this polynomial, and that's going to be that red distance. So what that would be this point on the red graph right here. And in that case, this distance right here would be p sub n of x. So that's going to be the distance. Now, notice the red graph only approximates the blue graph, and there's a difference between those two. And what that difference is going to be, we'll go ahead and mark that distance off here. That distance is going to be this black distance right here, and that's actually going to be what we're going to call the remainder. So r sub n of x. In this case, it's important to notice that's not just the remainder, that is the exact value of the remainder. So if I know p sub n of x, and I can get the exact value of the remainder, if I add the remainder to the polynomial approximation, I'll get the actual value. So now, what does this thing look like if you put it up here? So let's go back up to the top here, and what we'll do is this. So what is r sub n of x? It's just the continuation of all these terms. So I'm going to put a plus here, and I'll make this be, now again, if this was the nth term, this next term, I'm going to go ahead and write this one out. Everywhere you've got an n, just replace it with an n plus 1. So this is going to be n plus 1 of c divided by, and rather than n factorial, you'll have n plus 1 factorial. This one would be times x minus c raised to the n plus 1 power. And then finally plus, and I'll switch back to my little boxes again after this, plus this term, plus this term, plus this term, plus, and it goes on forever. Now what this would be, all of these terms together would represent the exact value of the remainder. So I'll put r sub n of x, and again I'll even include the word exact. So that's going to be the exact value. Now, when you start with a Taylor polynomial and you add the remainder, what you've actually got there, if it goes to infinity, is a Taylor series. And what that does, it changes this from an approximation, it changes it to exactly equal. So now you have the exact value of the function, and you can see that down here. So add the polynomial to the remainder, if you can get the exact remainder, and you'll have the exact value of the function. So that's where we are right now. Now the thing is how do you go about finding the exact value of the remainder? And you might remember at this point, it kind of helps to think, if you remember on an alternating series, you can find the remainder of an alternating series by just looking at the n plus 1 term. And the n plus 1 term represents the entire remainder. And you can do something like this, and this is where Taylor's theorem comes from. And it's all based on this. I think I'll just put a little red box around this thing. So if you just look at this n plus 1 term, it's similar, but not exactly to the alternating series remainder. But Taylor's theorem is based on the fact that you can use this term with a little variation to represent the entire remainder. So let's go ahead and try that. So it's going to look like this. If you look in the book, you will find that Taylor's theorem, so you've got Taylor's theorem, and what Taylor's theorem says is this. It says, and I think we'll go back to black again, it says that the remainder, r sub n of x, and I want to emphasize again, this is the exact value of the remainder, is equal to, and you just look at this n plus 1 term, it's equal to the n plus 1 derivative, and I'm going to leave this parentheses blank here just for a second, we'll come back to that, divided by n plus 1 factorial times this thing, so times x minus c raised to the n plus 1 power. Now the difference between the alternating series and alternating series remainder and Taylor's theorem to get a remainder is this. When you work with the alternating series, you would just evaluate this thing at C. But if you look carefully at the definition of Taylor's theorem, I think I'll put it in red so it kind of stands out here. What he does is this, is he replaces C with Z. Now, what does that mean? So what this is, this value here, and we'll kind of put a little red box around this whole thing. This is Taylor's theorem. And what it says is this, is you can get the exact value of the remainder if you were to evaluate the n+1 derivative at some point z. Now what z is, it's a number somewhere between, and I'll go back to here, it's a number between here and here. So between c and x, somewhere in here, and I'll just kind of arbitrarily pick it, is some value of x, which is z. And if you can find this particular value of x, you will be able, and you evaluate the derivative at that particular value of x, you will get the exact value for the remainder. So Taylor's theorem gives you a way of getting an exact value of the remainder. Now at this point, let's take a look at what we've got here. Is you were looking for an approximation. You wanted a Lagrange approximation, and what we've got instead is Taylor's theorem, which gives the following. You will know exactly what P is. You're going to know, if you can evaluate Taylor's theorem, you will know exactly what the remainder is. So if you know P exactly and R sub n exactly, you will get the value of the function exactly. Now at this point you should be thinking, well, wait a minute, if I can get all this stuff exactly, what do I need Lagrange for? Where does Lagrange come into all this? So far all we've done is looked at Taylor's theorem, and there hadn't been any thought of Lagrange at all. So let's move to the next page, and you'll begin to see where Lagrange comes in and why he's important. So let's do this. Now what I'm going to do is this. This is the part that we just got finished. We just got through showing Taylor's theorem, and here's Taylor's theorem right here. Now it's all based on this. If you can find a value of z and evaluate the n+1 derivative at that value of z, particular value of z, then that will give you the exact value of this thing. So this value of z is some number that could be anywhere between c and x, and somewhere in there, there's a value of x that will make this remainder perfect. But there's a problem with that, and I think I'll do it in, let's go down here, I think I'll do it in black. So the problem with this is this. If you're doing this, when it comes to just this term right here, you have to calculate z, and you're going to get an exact answer. So calculate z exactly. Now, the problem is this, is that on a lot of problems, it's going to be extremely difficult, and in some cases, impossible to actually find the specific value of z that makes this thing work. So I like to put a little thing right here, is this is going to be very hard in general. So the problem with Taylor's theorem is that while it gives you an exact answer, if you could find z, a lot of problems you absolutely can't find z, or you're going to have to go through a lot of work to get it. So this will give you an exact answer, but it's a real problem to actually work with. So where Lagrange comes in is this. Lagrange takes a look at Taylor's theorem and says, what I want is just an approximation. I've got an approximation for P, my initial polynomial, and I just want to know how good an approximation is it. So what I'm going to do is, rather than trying to find the exact value of the remainder, which is going to give you this black distance right here, and I think I'll go ahead and put that in there, so that rather than getting this black distance right in here, what he's going to do is this. He says, rather than calculating the exact value of the derivative, what I'm going to do is come over here, and I'm going to instead change the approach. I will estimate, so I will estimate the maximum value of the derivative. So what this one says is calculate the derivative exactly. Lagrange says, let's just estimate the maximum value of the derivative. And the nice thing about this is, you're going to see later on, this will actually turn out to be pretty easy. So it's a lot easier to estimate the maximum value of the derivative than it is to actually calculate that at z. But there's a penalty to be paid in that. If you estimate the maximum value of the derivative, and I think I'll do this in green, if you go down to here, what that means is this. So you're going to estimate the maximum value of the derivative, plug it into this thing, then when you evaluate this whole thing, what this is going to give you is over here you would get, and I think we'll do it in black, over here you're going to get the exact value of the remainder. You're going to get that black distance right here. Over here what you're going to get is an estimation. This is going to be the estimated maximum value of the remainder. So where Taylor's theorem gives you the exact remainder, but it's very hard to work with, Lagrange's theorem, Lagrange's remainder, or form of the remainder, it's going to give you an estimated maximum value of the remainder, but it has the advantage of being very easy to work with generally. Now, graphically, what it looks like is this. Let's just look at the numbers that we've got on here so far. So I'm going to go back to the graph, and I think I'll do this. I'll go ahead and turn this part off and actually turn the blue graph off too. And let's just start with this red graph. So suppose when you did the polynomial approximation, you came out with this value right here, and you came out with 4. Then you estimate the maximum value of the derivative, you compute this thing, and let's suppose that this thing, when you finally computed it, just to give it a number, let's suppose it turned out to be 3. So this is the maximum value of the remainder. So what this means is from this point, you would go up 3, so we'll go up 3 to right here, and we'll go down 3 to right here. So you can go from your initial polynomial approximation, go up and down 3. And what that's going to give you, I think I'll just do it like this, would be this. It's going to go a range, there's the top of the range, and then starting about right here, here's the bottom of the range. So what this means is that the actual f of x has to fall somewhere inside that range. And that's what the Lagrange remainder gives you. So all this means is that when you finally get around to doing the blue graph has to fall somewhere in between these green lines. So now let's turn back on what we did before and see how all this fits together. So if I turn on the blue graph, sure enough, and I think I'll turn this one off just for a moment. So sure enough, the blue graph does pass somewhere between the green line and the red dot. So it has to go somewhere between these two green lines, and it does. Now, if you put the previous work on there, and again, let's compare the difference on these two, is if you want the exact remainder, so the exact remainder is this black distance. And notice, the black distance is the exact remainder. This green distance is the Lagrange remainder, and look what the formula says up here. It says that the exact remainder has to be less than or equal to the Lagrange remainder. In other words, the black distance has to be less than or equal to the green distance, and sure enough, that's what it is. Now, to notice what happens when you change from Taylor's theorem into the Lagrange form, there's actually two changes that are made. First of all, rather than working with the exact value of the derivative, that's where this word max comes in. Rather than working with the exact value of the derivative, you're working with the maximum value of the derivative. So rather than calculating the exact value, which is hard, you're estimating the maximum value, which is easy. So that's the trade-off. Now, the other thing you lose is this, is you went from an equal to, if you calculated the exact value, it would be equal to. By switching to the maximum, it changes from equal to less than or equal to. So this is going to give you, the green line is going to give you the maximum possible error, but the real solution is probably going to be somewhere between these two green lines. And sure enough, it turns out to be about right here. So this is what we're going to be using, and actually it looks like it's going to be difficult to do, but you'll actually see that estimating the maximum value of the derivative is not as difficult as what you might think. So with this is what we're going to concentrate on, and it really comes down to, I think I'll put it in red here one more time, it comes down to this box. Is by evaluating what's inside of here, you'll get an estimate of the maximum value. Also notice it went and did this too. It picked up some absolute value signs here, and the main reason for the absolute value is it's possible if here is your estimate, this is your approximation. If the blue graph is above the red graph, you'll add these two together. So the red part plus the black part gives you the blue part. But it's possible that the blue graph might go below the red graph, and that's where the absolute value comes in. So whether it's above or below, the absolute value will take care of that and still just give you the difference between these two. So hopefully that makes it a little bit clearer about what all the different parts are. Let's go back and take one quick look at this. And again, so if you want to get the Lagrange remainder, you just estimate the maximum value of the n+1 derivative and then plug it into this thing, and that's going to give you your original polynomial plus or minus whatever this amount is, and you'll be done. Now, in the next video, we'll work out some problems, so I'm going to give you a sneak preview of that. We'll put a series of steps up here that look like this. And again, these steps look pretty intimidating at first, but you'll see to actually use these is pretty easy. So this is what we're going to do in the next video. So these steps will give you an approximate value of a Taylor polynomial using the Lagrange remainder. Now the first step is to go ahead and evaluate P sub n for whatever polynomial you choose. If you want a 4th degree polynomial, go ahead and evaluate that, and that'll give you your initial approximation. Then you want to know how accurate is that approximation. So you will use the Lagrange form of the remainder, which is what this is, to estimate that. So this is going to give you the two green lines. And again, to do this, it consists of these parts right here. So first of all, you'll find the n+1 derivative, which is going to be this part right here. You got to know what the n+1, the next derivative is. Then you'll make a reasonable estimate as to the maximum value of that thing, which will give you this part right here. Then once you've got this part, this and this are fixed, you'll evaluate this, and that's going to give you plus or minus some amount. And that's going to be the range of the error. Then finally, to find the final amount is starting with your approximation, you'll add that error and subtract that error to find the range of the values. So it's actually pretty easy to do, and you'll find that by just having to estimate the maximum value of this derivative, it's actually not a very difficult process. And we'll take a look at that in the next video. So hopefully that makes it a little bit clearer about what all the different parts of this thing are.